All right, we're going to go over just the practice for classifying rational and irrational numbers. The notes are pretty straightforward, so you can get into those other answer keys and fill in your notes on your own. So rational numbers are numbers that stop or repeat, whereas irrational numbers go on and do not repeat. So this first one, our example is 0.21. It's rational because it ends. That decimal does not continue going on forever and ever. Now, when it comes to a lot of these, I always say simplify them into either a fraction or a decimal in order to truly see whether the decimal stops, repeats, or if it goes on and does not repeat. So this first one, it's 3/12, which can be simplified to 1/4. 1/4 written as a decimal is 0.25. Because that decimal stops at that 5, that is rational. Our next one is 12 minus 2, which is equal to 10, as was said on one of the other notes pages that you should go back and fill in for sure, is that all whole numbers are rational. The next one, 8.33865 ... So that ellipsis, that ... means that those numbers continue going on. There is no kind of pattern in those numbers after the decimal, so this is irrational. The next one, we have 3.14141414. ... So the numbers go on and on and on and on. However, this pattern of 1 4 1 4 1 4 1 4 repeats, which means it is rational. 12.52, the decimal stops, therefore it's rational. Now, we looked at the next one in two different ways. So, or not next one, sorry, the next one is 0. 0 is a whole number, it is rational. It's the next one we looked at in two different ways. So, being as it is, 0.02202222. There's no repetition, but that decimal stops after the 2, which means it would be rational. If it had a ... the ellipses at the end, so 0.02202222. If it had that ... at the end to signify that that continues going on, there is no pattern in that 0.2202222, which would make it irrational. So you need to pay attention to whether or not the decimal stops, or if it has that ... that means it continues going. When it comes to radicals, this square root of 19 cannot be simplified. So if we changed it over into a decimal, it would have a decimal value that continues going forever without a pattern. So because we cannot simplify that square root, it is irrational. The square root of 32, if we simplified it, if we use the calculator, or however, if we use the factor ladder, if we did our factor ladder as review, take a 2 out of it, that gives us 16. 16 is a perfect square, which means 4 goes into it 4 times. So for every number you have twice, it moves to the outside. For whatever's left over, it stays inside the radical. So we still have a square root we cannot simplify. That square root of 2 makes this whole thing irrational, because the square root of 2 is a long, drawn-out decimal that does not have an end. So you guys can't read this next one on your paper, but it was 6,000 over 1. 6,000 divided by 1 is 6,000. 6,000 is a whole number, therefore this one is rational. For the next page, 8 minus 2 square root of 3. That square root of 3 cannot be broken down into a decimal that stops. It also does not repeat. So your square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, those are all these prime numbers. Well, 6 isn't a prime number, but it's all numbers that are inside the radicand that cannot be broken down into a whole number or a decimal that ends. So anytime you see those, it's irrational. Plus 8 and negative 2 square root of 3 are not like terms, so you cannot combine them. So looking at the expression as a whole, it is irrational. Our next one, 1.234. It stops after that 4, so it is rational. 8,876,546 is a whole number. Whole numbers are rational. Square root of 64 is 8 because 8 times 8 makes 64. 8 is a whole number, so the square root of 64 is rational. 1/9. 1 divided by 9 is 0.1111, repeating for all of time. So because it repeats, it's rational. So just like the next one, we have a decimal that goes on forever, but because these 7777777 repeats, it is rational. Square root of 2 minus square root of 2 equals 0. 0 is a rational number. Our next one is a fraction, 4 over 2 plus 5 over 2. Because they have the same denominator value, we can add the numerators and we end up with 9 over 2, which is equal to 4.5, which is rational because the decimal ends. It stops at a certain point. So there's no numbers after that 5, so it's rational. All right, pi times pi. Pi is an irrational. So if we do our irrational times our irrational, and it's specifically this irrational times itself, we end up with an irrational. So when in doubt, plug it into a calculator. When we plug this in a calculator, we end up with this really long decimal that has no kind of pattern. Okay, the next one. This simplifies to 2. We put it in a calculator. Also, square root of 8 divided by square root of 2 is the square root of 4. Square root of 4 is a whole number too. Because it's a whole number, it is rational. The next one, square root of 6 times the square root of 6. That gives us the square root of 36, which is 6. 6 is a whole number, so it is rational. All right, and this goes back to the sometimes always never chart that we filled in. And if you haven't gone back and filled it in yet, you need to do that. So rational plus irrational, that's like doing 2 plus 3, or even 0 plus 1, or 6 plus negative 4. If you complete any of those addition problems, you end up with a whole number, which makes it rational. Now, an irrational plus an irrational would be like doing 3 square root of 3 plus 2 square root of 3, which would give you 5 square root of 3, which is irrational because it has that square root of 3. Now, irrational times irrational. This would be like doing 2 times 3. which is a whole number 6. Or doing -6 times 4, which is -24. They still all end up as whole numbers, so those are rational. An irrational times an irrational. So this is where things get a little funky. So if you have square root of 2 times square root of 3, that equals the square root of 6, which is irrational. However, if you have the square root of 2 times the square root of 8, that gives you the square root of 16, which is 4. 4 is a whole number, so it's rational. So when you multiply an irrational times an irrational, sometimes you end up with an irrational answer, an irrational product. Sometimes you end up with a rational product. So the next one, irrational times rational. So sometimes you'll have something like square root of 2 times 4 gives you 4 square root of 2, which is irrational. But if the rational number you're multiplying by is 0, square root of 2 times 0 is 0, which is rational. So that's another one where it can go either way. So the product of an irrational and a rational can be either irrational or rational. So irrational divided by irrational. This would be like 1 divided by 9. We already saw that problem up top. We already showed that it is a rational answer. So if we did 2 divided by 4 equals 0.5. No matter which way you do these, you're going to end up with a rational. Lastly, we have an irrational divided by irrational. So if we have square root of 2 over square root of 3, that would be irrational. If we had the irrational square root of 3 over irrational square root of 3, that equals 1, which is a whole number. So it means it is rational. So the next page is something for you to use to practice this and recognizing when a decimal ends or when it continues going. Is there a pattern? Is there no pattern? Is there a square root that cannot be simplified into a whole number, etc.? So I want you guys going through this one, practicing, and then checking your answers.